Fischer Esterification, Emil Fischer, but here Fischer means sulfuric. That's how you can remember. Fischer sulfuric. That means H plus slash HSO4 minus. It's similar to HA, but it's never hydrochloric acid. It is wrong. Hydrochloric acid cannot be the catalyst here. It cannot be the water scavenger. So the sulfuric can do both things. That's why sulfuric is the catalyst in this case. So that's the Emil Fischer's findings 200 years ago. And what he did, carboxylic acid, alcohol, heated with sulfuric will end up with an ester and byproduct water. I wouldn't pay much attention to draw the water because you might not get much marks on it, but the rest is important. Carboxylic is an oic like ethanoic, alcohol is an ol, something like ethanol, and the ester is something like, in this case, let's say ethanoate, and the alcohol is like something like methyl ethyl. So that's how you kind of want to remember. Also remember, these OHs reminds you hydrogen bondings. They are very polar, acid and alcohol. Ester don't have it, so it's less polar. So that's another thing you want to know for the multiple choice questions, right? And also just try to keep this picture in your memory. The acid and the alcohol, and you remove the water, box out the water, and also see the colored oxygen that coming from the alcohol. That's important for the Emil Fischer's esterification mechanism. So the byproduct water, it's there, right? Now, so we're going to look at few examples. This is ethanoic acid, and this is ethanol, and again catalyst sulfuric. Boxed out the OH and H. In this case, see OH coming from the acid, and you draw the ester, and the H coming from the alcohol. So ethanoic gives you ethanoate in the product, and ethanol gives you ethyl in the product. So you name as ethyl ethanoate. Now look at this case, again ethanoic acid, and this alcohol is isopropanol, and you box out the water, that's the byproduct minus water, and then you draw the product connected, that one, and then the oxygen from the alcohol. This is actually 2-propanol, and the acid is ethanoate because it's ethanoic acid. The alcohol is 2-propanol, it's called 2-propyl ethanoate. Now it's actually isopropanol, that's like smells like hospital basically, but its esters are sweet smells, fruity smells. I'll mention you later. Now benzoic acid and ethanol box out the water, and you get benzoate, right? Because the benzoic acid gives you benzoate from the benzoic, and the ethanol will give you ethyl here. So ethyl benzoate, right? Now let's look at a few other examples. Now here I have ethanol, again another way to draw it, but it's 4 carbons butanoic acid and ethanol. Look at this one, a little more carbons, actually 2 carbons more, hexanoic acid and ethanol. Look what happens. Again, sulfuric acid box out the water. Look at the pattern, always box out the water, and put together the 2 pieces, and then you have the 2 esters. Now what's the fundamental difference is 2 carbons, right? But the first one will give you the banana smell, and the second one will give you the pineapple smell. But try to write the names of those 2 esters. Now the final one, the yellow one, if you did learn intermolecular, then learn it, otherwise don't. So what happens here, you have the alcohol and the acid together, and alcohol nucleophile attacks on the electrophilic carbonyl, and it makes the intramolecular lactone or cyclic ester. So this one is called the cyclic ester, and depending on number of carbons, it's called the gamma lactone,